Okay, hi everyone. Any questions before we begin? Last class we were reviewing synthetic controls. Okay, great. So today we will be reviewing a paper about synthetic control, and I will show you some code on Stata on how to actually run one yourself. And then that should take us about I don't know, like 45 minutes, and then we'll go into the next chapter, which is regression discontinuity design. So RD. I'm sure you guys have seen it before, so it should be a nice review. Yeah, so that's the plan. Just remember that the next thing due for you guys would be the referee report, but we moved it back to June 5th, I think. So it was originally supposed to be due on the 29th in 2 days, but like as the note says on SIGA, we're moving it back until June 5th, so you guys have more time. So just when you complete that, make sure you can send it to me via email and your name is on the document and all of that, and we'll be good to go. And then I will be handing out your final assignment probably tomorrow. So you can do that again in pairs because that seemed to work well. And it's less marking for me, so I'm happy about it. So yeah, I'll hand that out maybe tomorrow. And you'll have until the very end of the semester, like June 14th, I think. Okay, I'm going to share my screen then. Was there any questions about synthetic control that we reviewed on Monday that you guys would like to go over again today? Okay, so the basic principle of synthetic control, remember, was that it's basically would be the same setup for a difference in differences. So normally it's like a policy at the aggregate level, so whether it be a state or district or school or community or something like that. And so they're going to receive a program or policy implemented in one time period. And so you will have a pre-period and a post-period for your treatment group. And instead of comparing the treated district or unit to a randomly chosen control group, so instead of saying, oh, we're going to compare like Piura to Chiclayo or something like that, like one state to another, it can be kind of random and it's not really based off of anything, right? So maybe a better way to optimally choose your control group would actually just be to synthetically create one. So this is what the synthetic control method does, is when you have a treatment group and we're trying to match a control group that doesn't really exist, but we're going to combine a bunch of different characteristics of different untreated units. And so all of those characteristics will weight for each group so that the characteristics of our synthetic control look identical or almost identical to the treated unit. Okay, so to do this, you'll have to have a set of x's, which we call our predictor variables. So they're going to predict the outcome of interest. So it could be like demographic factors like age, income, industry type, like whatever the outcome in it is, it will depend what predictor variables are important. So based on those predictor variables, you'll give different states or units of untreated groups different weights to basically match the treated group. So then we could do like a balance table, the same as we did in randomization, between the treated group and the synthetic control group made up of all of the different untreated units. And so you want to see that all of those characteristics of the predictor variables are matched between the treatment group and the synthetic control. So it's very similar, and also I would say it has basically the same assumptions, identifying assumptions as the difference in differences, because, well, you need pre-trends, right? You need common trends for this control group to be valid, because similar to a difference in difference, we're using a control group to estimate the time trend, right? Because, well, I have a question for you guys. Why can't we just estimate the time trend using our treatment group? Why do we even need a control group? Why can't we just use the treatment group?
Sorry, can you repeat?
Oh yeah. So I said we need the common trends assumption to be held for the basically causality to be held. So why do we even need the control group to approximate the time trend for the treatment group? Why can't we just use the time trend for the treatment group itself and not have a control? What would be the problem with that?
That there may be other factors that affect both groups after the control, after the t equals 0.
Right, yeah. Well, the problem is that we have the treatment effect on our treatment group, right? So we won't be able to separate the true effect of the treatment from the time trend. So that's why we need to be able to separate the treatment effect from the time trends by saying what the time trends are for this control group. So that's really what we need to do, differentiate the treatment effect from the time trends. But since we never observed the treated group, their time trends on their own, we need to say, okay, well, we've created this identical group using our synthetic control. And since their characteristics are identical and their trend lines of the outcome seem to be moving the same, then we can say that this outcome can approximate the time trend for the treatment group. So that's really the function of the synthetic control, and it's the exact same as the difference in difference. The only difference really is that you're using a made up group, like you're making it up of a bunch of different characteristics of many untreated units. So yeah, that's why it's synthetic. Okay, so that's about all it is, pretty straightforward. So this paper is by Abadi et al. In 2007, and it's called Synthetic Control Methods for a Comparative Case Study, Estimating the Effect of California's Tobacco Control Program. Have any of you read this paper or no? No. Great. Oh, wait. No, okay. That's kind of cool. So this paper is investigating the application of synthetic control methods to comparative case studies. So the authors are discussing the advantages of these methods and apply them to study the effect of this Proposition 99. So Proposition 99 was a large-scale tobacco control program that California implemented in 1988. Okay, so 1988, they implemented this tobacco control program basically to reduce tobacco consumption in California. That's when it was just starting to become like a big health concern. So social scientists are often interested in the effects of events or policy interventions that take place at an aggregate level and affect aggregate entities such as firms, schools, geographic areas, or administrative areas, so country, regions, cities, right? That's what we talked about. So we looked at difference and differences so far, and we also looked at synthetic controls as another way to address this. And so this is an example, the difference in difference, and I would also say even synthetic control is an example of comparative case study. So a comparative case study involves researchers estimating the evolution of aggregate outcomes for a unit affected by a particular policy change or some event or intervention of interest, and they compare it to the evolution of the same aggregate estimates for a control group, so for an unaffected area. So that's the same as we say any policy is implemented, like we talked about the minimum wage paper. So New Jersey saw a minimum wage increase, and we looked at how that affected teen employment in fast food restaurants. So we look at the whole evolution of teen employment in fast food restaurants from before the implementation to after. And so we're comparing that to the control group, who does not receive a minimum wage change, but they still obviously have maybe changes over time in teen employment based on the economy or other factors. So that would be a comparative case study, because you can see it's a case study. It's not encompassing the whole population. It's just looking at two very specific states and one very specific occurrence of a minimum wage increase. So it might not be perfectly externally valid because obviously it's a specific situation. That's what makes it a comparative case study. Okay, so aggregate data is often really a lot easier to collect than micro level data. So like panels of data over time at the individual level, those are more rare and often private. So given the widespread availability of aggregate or macro level data, so at the school, city, region level, so like in NAHO, they have data at the household level, right? But I mean, they don't follow each household year by year, they just randomly sample households. So that wouldn't be micro level, right? That would have to be aggregated to some like district level at least, because you can't say each household you have data for each period. So then you have to go to the next larger unit. Okay, so it's also nice because so many policies obviously occur at an aggregate level, like at city or district or province or country. That makes comparative case studies really nice, and we see a lot of them in economics. So the only problem is that comparative case study research is limited in the social sciences by two problems that affect its empirical implementation. So first, in comparative case studies, there's typically some degree of ambiguity about how comparison units are chosen. So we talked about this last class. With the difference in difference, we think about the methodology, but we actually don't really think much about the choice of a control group, right? That's never a huge part of the conversation. But you want all of your choices when you're doing a research to be data-driven and driven by empirical reasoning. So when you just randomly choose a comparison group, it's really hard to justify. I'm sure if you guys are doing your thesis and you state what your control group is, your supervisor will probably say why, like why did you choose this? What made your decision? And it is really important because you want your control group to be as comparable as possible. So yeah, researchers often have in the past chosen comparison groups on the basis of subjective measures between affected and unaffected units. So, oh, well, these two states are really close to each other, so they probably have similar economic shocks. Well, that might not be true if one state is really heavy in one industry, whereas another state is concentrated in another industry. So there could be different types of shocks that affect them differently. So it might not just be enough to say that, well, they're close to each other, so they're the same. Okay. Secondly, even if aggregate data is employed, if we're using it, there remains uncertainty about the ability of the control group to reproduce the counterfactual outcome trajectory that the affected units would have experienced in the absence of the intervention. So, I mean, that's the whole issue of causality. Is our control group similar enough to our treatment group that they can actually predict the counterfactual? That's the big question when you're looking at causality as an economist. How is your counterfactual good enough? If not, obviously your results are going to be biased and you can't trust whatever estimates you find. So it's really important to know. So this is uncertainty that would not really be reflected by the standard errors with traditional inference for comparative case studies, because I mean, you're just assuming that the counterfactual is as it is, so it's not going to be reflected in a larger standard error. Okay, so this paper is offering a synthetic control comparison. It's definitely offering a critique against the classic difference in difference case study design, and really pushes towards favoring a data-driven procedure, which is basically forcing the choice of the comparison group to be a function of how related the affected and unaffected units are based on characteristics that you can actually measure. So they're completely making this comparison group choice based on existing data of pre-trends. And I mean, it's definitely easier to find a control group that way, because pre-trends is the whole, like having parallel trends is the whole identifying assumption of difference in differences or synthetic control. So do you think it would be easier to have to randomly choose a state that hasn't been treated and check to see if their trends and outcome are precisely parallel? Or do you think it would be better to synthetically create one by making sure all the characteristics are same to begin with and then checking? I definitely think like the second one is a lot more control, whereas the first one is a bit of luck. Okay. So the idea behind the synthetic control approach is that a combination of units often provides a better comparison for the unit exposed to the intervention than any single unit alone. So if we have 20 untreated units and we can find some sort of linear combination of each one to create a synthetic control for the treated group, more times than not, it's going to be better than just having one unit as a control group. Okay, so the synthetic group control is a weighted average. So it's a weighted average of all the untreated units that you're including. And that doesn't mean they're all going to be perfectly weighted, right? If one state, for example, seems to not be related at all to the treatment group, it's probably going to get a weight of 0, so none of its characteristics are included in the synthetic control, just because it's not similar enough, okay? And on the other hand, like it might be the case that you can't even create a synthetic control using all of your control units if your treated unit is such an outlier that you can't make any linear combinations of the untreated units to form a comparable synthetic control to the treated unit. Does that make sense? Okay, great. Oh, can I repeat? Yeah. So the first the first example I said is that most of the time it's going to be better to create some linear combination of all of the untreated units to form a comparison group for the treated unit than just using one single untreated unit alone, right? Because what is the probability that one treated unit will be similar to one untreated unit compared to one treated unit compared to 20 other untreated units that we can combine in such a way to optimize their similarity to the treated group, right? It's just way more likely that when we have more data points, we'll be able to create a better comparison group. than just using one group alone. So that's really the reasoning of a synthetic control. But my second point was that there are some cases when you can't even use a synthetic control to create a good counterfactual when your treated unit is such an outlier, because when it's an outlier, its characteristics are really, really different from the other groups. So when you're creating a linear combination of the two groups, you want the characteristic of the treated group to be in between two other groups, right? So then you can take a linear combination and find somewhere in the middle. But when the characteristics of the treated group are way, way outside those of the untreated groups, then it will be impossible to make a linear combination. And so we might not even be able to make a comparable synthetic control. So that would definitely be a challenge. And it would threaten the validity of your synthetic control, but it still might be better than just choosing one unit alone. It's hard to say. So just keep that in mind. Okay. So because the synthetic control is a weighted average of the available control units, right? So out of all the different control groups we could use, we make a synthetic control as a weighted average of all of those groups. So this makes it really clear the relative contribution of each control unit to the counterfactual, because we can see how much of a contribution each group is making to create the synthetic control. We can say, oh, well, this group got a weight of 20% of the synthetic control. This group only got 1% of the weight, and so on. So it's very clear how your control is created. And then also, it's also very clear the similarities or the lack of similarities between the units affected by the intervention and the synthetic control in terms of pre-intervention outcomes. Okay, so obviously, when I say we're trying to make a comparable control group on the basis of the treated group's characteristics or predictor variables, that's only for the pre-treatment period, because we don't want to compare them to post-period after they receive treatment, because that's when we need to look at the treatment effect. So we're only interested in matching the treatment group to a synthetic control in the pre-treatment period. So we make that period look identical in terms of characteristics, and then we know that we have a good comparison group to approximate the counterfactual in the post period. And then we can difference out the true treatment effect, right? Because the only difference between the treatment group and the control group is that they have the same time trends, but the treated group also has a treatment effect on top of that. So we are interested in finding the treatment effect. So we need to difference off the time trend. So that's what the synthetic control will serve in the post-treatment period.
I have a question.
Yeah, let's hear it.
So in practice, you will collapse all the observations of these weight average into one observation, or the output is going to be weight? How is?
You mean in terms of data analysis?
Yes.
No, it's actually really simple. Like I'm going to show it to you guys after I do this paper. You don't need to collapse any variables to the means. There's actually a command called synth, like synth, and you'll write synth, and then you can choose all of your predictor variables. And then you choose your treated unit and the time of treatment. And so based on that, it will look at the pre-treatment period and decide what states are most related to the treatment group and give them all a weight. So it's actually really compact and easy and data.
So it's kind of automatic, like giving the weights?
Yeah, it's really automatic. I'll show you guys in like 10 minutes.
Thanks.
No problem. Okay. So yeah, I mean, this is just a review of what we talked about on Monday. This is the paper's empirical strategy. It's basically the empirical strategy I showed you in general. So remember that we observed J+1 regions. In this case, will be states because we're looking at the US. So the treated unit is J=1, and then the other J units are untreated. So J=1 is California, and then J=2 to J+1 is all of the other states included. I don't think they use all of the states in the US. They only use like 30 or something. I think they exclude ones that have also received some sort of similar smoking policy in a similar time period. Okay. So let yn for it, so state I in time t, be the outcome that would be observed for region I at time t in the absence of the intervention. So this is our basically the potential outcome for our synthetic control. This synthetic potential outcome for synthetic control. And then we have y1 it, which is the potential outcome which the treated unit observed. So that's these are both our post-period outcomes. So these are the effects we're really interested in. Obviously, we need to estimate this because we're using a synthetic control, so we don't observe it. So this is what we're going to estimate. So let W be I think that's J+1 vector of positive weights that sum to 1. So we have W is a vector of weight. So each control state is receiving a weight based on how similar they are to the treated unit. So that's just going to be W is equal to W2 all the way up to WJ+1, right? So those are our control groups, and that's the weight that they receive. So if WJ equals 0, oh wait, no, greater than 0. Greater or equal to, sorry. That should be greater or equal to. That's because sometimes the weights can equal 0 if we think they're not related at all, and sometimes they can be greater than 0 if we think that they're related to the treated group or can help become a synthetic control. It's never going to be less than 0, it's always going to be greater or equal to. So that's here, Wj greater or equal to 0. For J = 2 to J+1 for our control units. Okay. W2. I don't know what this, ignore this, I don't know what I was trying to say here. Okay, so each value of W represents the weighted average of the available control regions and therefore a synthetic control, right? So W2 is the weight that we're giving to unit 2, so the treated unit 2, untreated, sorry. And then Wj will be the weight that we're giving to the untreated unit J. Okay, well they're saying, yeah, I guess you can use negative weights, but it's not that common. Okay. So let characteristics be a vector x. So those are, our x's are our predictor values. So x0 is a vector of characteristics for the control group, and x1 is a vector of characteristics for the treatment group. Okay, you guys need to hang with me because my latex is really bad here. I'm just missing all of my characters, so I'm sorry, I'll have to go back and fix that. So yeah, we have x0 is the vector of characteristics or the predictor values, they're the same, for our control group, and then x1 is the predictor values for our treatment group. So the vector W, so the vector of our weight, is chosen to minimize the distance between x1 minus x0W. Okay, so the characteristic for the treatment group minus the characteristic for the control group given some weight, right? So we're trying to choose our weight given by this function, minimization of the distance between x1 and x0 times W. Okay. Subject to that, the weights are greater or equal to 0. and then all the weights combined have to equal to 1. Is there any questions on this notation? Okay, so then I assume it's clear. We're just trying to minimize the distance because that makes the two groups look as similar as possible, right? When we're subtracting the two, if 1 minus 1 equals 0, that means they're basically the same. So we want the characteristics between the two groups to be as similar as possible. Okay, then let the observed outcome for unit I at time t be yit equals yitn. So this is the potential outcome for the control group plus alpha it dit. So this, there shouldn't be an it there, alpha dit. Okay, so alpha is just the coefficient, and dit is the dummy, equals to 1 if, okay, yeah, if I equals 1 and t is greater than t0, that's greater. Okay, so we're basically saying that the outcome that we observe for the treatment group is a function of the potential outcome when you're not treated, which we're estimating using our synthetic control, plus the treatment effect, right? So that's very straightforward. That's basically the same as we've looked at before, but using expected outcomes. And t greater than t0, so t0 would be the time of treatment. So we're looking at the post-treatment period, right? We don't want to compare the difference between the two groups pre-treatment. We only care about post. Okay. Oh, wait, what? Oh. Wait. 1 second. My mind. Okay. Oh, yeah, I see. So what we estimate here, our treatment effect is just going to be the difference between the outcome for the treatment group minus the outcomes for the control group. So basically we have the weight of, let's say, unit J, so that's the control group, and their outcome for unit J, right? So we chose the weight based on the pre-treatment characteristics, our x's. So now we're just taking that same weight and applying it to our y, because that's what we're saying, okay, well, this is how important it is to describe our treatment variables. So we're going to apply the same weight to our outcome. And so we'll take the difference between the outcome for the treatment group and each outcome for the control groups given their W's. So given their weight. And then that's for all of the control groups, we do that. So J equals 2 to J equals J plus 1. Okay. Okay, now to the paper. So obviously you guys remember this is a paper on a smoking control program. So anti-tobacco legislation has had a long history in the United States. So it dated back to at least 1983, when Washington became the first state to ban the sale of cigarettes. Over the next 30 years, 15 other states followed with similar anti-smoking measures. They were primarily motivated for health reasons. Oh wait, no, for moral concerns. Health was secondary, so that's interesting. Almost 100 years later, what's that?
What do you mean with moral concerns?
It's just like smoking is associated with like sinning, I guess. I don't know if it was like a Catholic or Christian push towards, oh, like you're sinful if you smoke, like it's not the right thing to do, it's not proper. So I guess that's what they're referring to. Like in that time in the United States, Catholic had a big influence. Even like in the 1920s in the United States, they had a prohibition of alcohol. And that wasn't because they cared about people's health, that was because they thought alcohol was evil and not the right thing to be doing. So I think it's kind of the similar sentiment.
Okay.
Yeah. So almost 100 years later, after these early laws had long since been repealed, so obviously Americans weren't for that. They started smoking again. The laws in the 1890s went away. Um, but 100 years later, widespread awareness of smoking health risks started a new wave of state and federal anti-tobacco laws across the United States and then overseas around the world. So leading this wave in 1988 was um, a program in California, which was voted in. So it was voted by California people, and it was known as Proposition 99. So this was really the first modern time large-scale tobacco control program in the United States. So this is what they do their analysis on. So this Proposition 99 increased California cigarette excise tax by 25%. No, 25 cents, sorry, per pack. And then they used the tax revenue to promote health and anti-smoking education. They funded anti-smoking media campaigns, and they created local clean indoor air laws. So basically, you're now no longer, not only are you getting taxed more on cigarettes, but you also can't smoke inside. There's more awareness to anti-smoking and such like that. Okay, so upon initial implementation, Proposition 99 produced more than 100 million per year in anti-tobacco projects for schools, communities, counties, and the state level. So that's just from the profits from the taxes. Before Proposition 99, no city or town in California required restaurants to be 100% smoke-free. But from 1989 to 2000, approximately around 140 laws were passed. So this was a really big reform. Like this is super large scale. And by 1993, local laws prohibiting smoking in the workplace protected nearly 2/3 of workers in California. So no smoking in restaurants, no smoking in workplaces. So most public buildings you can't smoke, which is crazy because, I mean, I don't know about you guys, but when I grew up, I remember going to restaurants and they would have areas where you could smoke inside, which is totally illegal in Canada now. Like you can't smoke in any public place. But yeah, I was like 5 years old and you go into the restaurant and there'd be a whole smoker section of men smoking their cigarettes. So times have really changed. So yeah. So before Proposition, wait, did I say that? Oh yeah, I said that. Okay, so Proposition 99 was widely perceived to have been successful at cutting down smoking in California. So after the passage of Proposition 99, that was in 88 through to 1999, adult smoking in California fell by over 30%, and youth smoking dropped to the lowest level in the country, and per capita cigarette consumption more than half. So it seems like even the people that were still smoking are smoking less volume. Okay, so prior to 1988, which is the treatment year, per capita cigarette consumption was around the national average at 22.5 packs. I don't know if that's per month. 10 years later, per capita consumption was 40.4 packs, lower than the national average. So before the policy, it was right at the national average, and then afterwards, it took a real decrease in average of packs per, I think it's month. Actually, is that a lot? That's like a pack per day. I don't know. So the authors want to estimate precisely the true effect of the statewide program on smoking behaviors. So, I mean, this, what we've talked about, it seems like there is evidence that this policy has been effective, but they're trying to actually estimate the true impact of this program on smoking behavior. Okay. So the authors are using annual data at the state level and this panel from the periods 1970 to 2000. So this proposition was passed in 1988 and went into effect in 1989. Okay, so it actually went into effect in 1989. This gives the authors 19 years of pre-intervention data, right? So they have from 1970 to 1989. The sample period begins in 1970 because it's the first year for which data on cigarette sales are available for all the control states. So, I mean, that's pretty early to start anyways. Not many people have 19 years of pre-intervention data, but they couldn't get any sooner, so that's what they do. And then it ends in 2000 because at this time, other anti-tobacco measures were implemented across many states. So then if you go further than 2000, you can't use these states as a control group because then they're affected by their own policy, right? And what do we need to have from a control group to be valid? That they're not treated. So yeah, it's really hard to measure the effect over a policy over really long periods of time just because the control groups might start receiving policies of their own. Okay. So yeah, so the synthetic California is constructed as a weighted average of potential control states, and then weights are chosen so that the resulting synthetic California best reproduces the values of a set of predictors of cigarette consumption in California before the proposition of 1999. And so they just drop other states that had similar tobacco programs within the period of analysis. So their outcome variable is annual per capita cigarette consumption at the state level. So it's measured in terms of per capita cigarette sales in packs. A disadvantage of the tax revenue-based data relative to survey data on smoking prevalence is that the first one, the tax revenue-based data, is affected by cigarette smuggling across tax jurisdictions. So if there's higher taxes in California than a neighboring state, maybe some people will think it's worthwhile to cross the border and buy cigarettes from there. And what would be the problem with that? So what would be the problem if people in California responded to this law by simply going over the border to buy cigarettes in another state?
The results could be biased.
Yeah, absolutely. Your results could be biased. I mean, if you guys ever don't know what to answer to a question, just say that. You're 100% right. But yeah, because if these people are going to the state, another state, and buying cigarettes there, we're going to have a biased estimate because the cigarette sales in California drop, but then the cigarette sales of a neighboring district or state go up. So then we're going to have a super overestimated effect because we're going to say, oh, well, this state, their consumption went up over time. So then you see an even bigger treatment effect. And then, like in California, people are still smoking. They're just going across the border to get cigarettes. So there's not actually a positive effect on smoking or health or whatever. So yeah, it would completely bias the results. So they include in X1 and X0, so the characteristics for the treatment and control group, the values of predictors of smoking prevalence for California, and the 38 potential controls. So their predictors of smoking prevalence are average retail price of cigarettes, right? So obviously the reasoning for that is if cigarette prices are lower, people are probably going to buy more, right? Supply demand. Per capita state personal income. I wonder what relationship do you guys think those would have? The relationship between income and cigarette consumption. Do you think it would be positive or negative? Negative? I don't know. I would think negative too. Maybe positive. Ooh. It's hard to say, right? Because if you have more income, you have more disposable money to spend on cigarettes, right? Because cigarettes are not essential. So if you really don't have money, you're not going to spend money on them. But on the other hand, like if you think about a lot of high income people, maybe they have more money to spend on investments to health. So they'd be maybe less willing to buy cigarettes. And also maybe if you have higher income, you're more educated and you know better about the negative consequences of cigarettes. Yeah, a good question. I'm going to be thinking about that. I guess we can check the data. Okay, so yeah, then the percentage of the population aged 15 to 24. So basically youth, because obviously youth tend to smoke more, I guess. I mean, not anymore really, but in the day they did. It was the cool thing to do. And then also per capita beer consumption, because they think that like alcohol and cigarettes are complementary goods. So if someone's consuming beer, they'll probably consume cigarettes, but I don't know. I'm sure there's some positive correlation there. These variables are averaged over 1980 to 1988, and they augmented by adding 3 years of late smoking consumption. Okay. So figure 1 plots the trend in per capita cigarette consumption in California and the rest of the US. So let's do this. So this is figure 1. So it's showing us per capita cigarette sales, the California versus the rest of the US. So what do you guys observe based on this trend line? So it's from 1970 to 2000. I don't know. So do you think that they trend similarly? Any comments in general that you would like to make?
It appears that they were quite similar at the beginning, but then they start diverging.
Yeah, I totally agree. Like they do look pretty similar. I mean, California has seemed to always had lower smoking rates than the rest of the country, except for like the very beginning period. You can see that at 1970, California actually had slightly more. There's a decrease in trend for both groups, but they might not be identical. Like it might not be an exact parallel trend, because you can see that the two groups are kind of diverging from each other even before the policy hit. So is this actually a treatment effect, or is this just different smoking trends between California and the rest of the US without any intervention even, right? So is it selection bias or is it causality? So as the figure suggests, the rest of the United States may not provide a suitable comparison group to California to study the effects of Proposition 99 on per capita smoking, because even before the passage, even before the law passed, it seems that cigarette consumption in California and in the rest of the US differed quite a bit. So to evaluate the effect of Proposition 99 on cigarette smoking in California, the main question is then how cigarette consumption would have evolved in California after 1998 in the absence of Proposition 99. That's our counterfactual, right? We want to know what would have happened to California in the absence of the program. So how are we going to estimate that? We're going to use, well, the authors are going to use the synthetic control method. Okay, so the synthetic control method provides a systematic way to estimate this counterfactual. So the authors are constructing the synthetic California as a combination of states in the donor pool. Remember, we call donor pool the whole group of untreated units. So those are all the states. I think there was 38. So in the donor pool that most closely resemble California in terms of pre-Proposition 99 values of smoking prevalence predictors, right? Remember, we're using our set of X's, the predictor values. So I think they had the list, we already talked about it. So that was like beer, price of cigarette packs, income, the age group being 15 to 24. So all of those are their predictor variables. So they show the results in table 1, which compares the pre-treatment characteristics of California with the synthetic control, or synthetic California. Okay, so this is what we have. So this is real California, and this is synthetic California, and these are all of their predictor values. So log GDP per capita. Oh, I thought it was individual income. That makes more sense. Percent age 15 to 24. Retail price, beer consumption, so, and then cigarette sales in 3 different years, so 1988, 1980, and 1975. Okay, so you can see by giving them specific weights, how does it look? They look a lot more similar than if you were to compare real California to just an average of all 38 control states, right? So the difference, do you understand the difference between synthetic California and the average of the 38 control states? If so, what is it? What is the difference in the basically composition of the synthetic control group versus just taking the average of all of the control groups? Well, we got a chat. Weights are different than the simple average, right? So a simple average, we're weighting each control state equally. In a synthetic control, we're weighting each state based on how related they are to the true treatment group, so California. So that's why you can see that, I mean, some of them are pretty similar if you just use the average, but like this is noticeably different. Retail price, right? You can get the synthetic group really closer in characteristics than the average. Same for beer consumption, same for cigarette sales per capita. So you can see how it actually does make a big difference using the synthetic control to just the regular diff and diff. Yeah, Nicholas Castillo says the weights are picked in order to minimize the difference of the synth control and California. Exactly. So remember the minimization function? It was that you want to minimize the predictor value of the treatment group minus the predictor value of the control group multiplied by some weight. So the weight is what we're trying to obtain. And yeah, the weight for an average is just going to be equal for each unit. Okay, so let's take our 10 minutes here, and then I'll see you guys at 7:09. Okay. Okay, so yeah, we just looked at table 1, which is looking at the predictor means for our synthetic control group compared to California. And we can clearly see here that creating a synthetic control is much better than just averaging all the control states. Okay, so this would be a common difference in difference method sometimes. Like, I know the cases we've talked about have only been one treatment group, one control group, but you can take an average of multiple groups. So that is still a difference. And it can still not be as um, accurate of a control group as the synthetic control can. So just keep that in mind. Okay. Then table 2 displays the weight of each control state in the synthetic California. So the weights reported in table 2 are showing that smoking trends in California before Proposition 99 is best reproduced by a combination of Colorado, Connecticut, Montana, Nevada, and Utah. Okay, and then all other states are actually assigned a weight of 0. So we'll see that right now. Okay, so this is the table of the weights that each state were assigned. You can see the state and the weight. So there's a lot of zeros, they're not included. And then we have weights given to the ones that are included that are greater than 0. So Colorado is given a weight of 0.164, Connecticut only less than 1%, or no, 6%, so 0.069. And then Montana 0.199, so about 20%. Nevada 23.4%, Utah 33.4%. So all of those need to add up to 1. 30. Yeah. Doesn't seem like that adds up to 1, but anyways. So that's why it's like so concrete. When you create a synthetic control, you can know exactly what control units you're actually using. So it's very transparent in your analysis. Okay, so this is what they create as their synthetic control. So they're mapping out the trend in per capita cigarette sales, California versus the synthetic control. So you can see this is much better than the last graph we looked at. Remember here, this was when we just looked at the average of the rest of the US, right? So in comparison, the pretreatment cigarette sales looks a lot better, right? So they look basically identical, except for this first period in 1970 where there's that small gap. But other than that, like, I mean, if you're asking for pre-trends, you really can't get better than that, in my opinion. I don't know if you guys agree with me or if you have any disagreements, but those are pretty parallel. You can see they're even like, there's some cycles here and they're moving very similarly. And then you can see there's only a split between the treatment and control group at the time of treatment, really, right? So this is at 1989. And so after 1989, so this is the post-treatment period, and this is where we'd be measuring the treatment effect of the policy. Okay, next graph. So yeah, that's displaying the per capita cigarette sales for California and the synthetic control during 1970 to 2000. And then as we saw, this definitely looks like a very closely related pre-trend compared to when we just looked at the average of all of the other 38 states. Okay, so subsequently, their estimates of the effect of Proposition 99 on cigarette consumption in California is the difference between per capita cigarette sales in California and its synthetic version after the passage of Proposition 99. Okay, so we're just looking at the difference in the two lines, actually. Remember how in a difference in difference, we did the before minus after for the treatment group, and then minus the before and after for the control group. So this, you don't actually need to do that. I mean, there might be some papers where authors have if the pre-trends aren't so exact, but you can see in this paper, the pre-trends are so precisely identical that it wouldn't make any difference for if you just took the difference and means in the after period, or if you did a proper difference and differences, because their pre-period cigarette sales are identical, right? So there's really no justification for doing the difference and difference method. Oh, I just realized I have chat. Oh, no problem. Okay. So yeah, so this analysis, they are just simply matching the pre-trend characteristics using the synthetic control, and they're so precise that you just need to take the difference in means in the post period for causality. So based on the difference in lines, what do we see? We see that this is California, the black line, and this is the synthetic California. You can see that there's a large negative decrease in cigarette sales from the policy, right? So we would take that as a causal effect. We can see that there's a large decrease in the cigarette sales per capita between California and the synthetic California. And then what else do I want to say? I don't think anything on that. Okay. Okay. And then this is just the difference between the two, but they're just making 0. So this 0 is the trend of the control group. So they're just normalizing the difference or showing you the line that is the difference between the two, right? So remember 1970, we saw there was this gap here. So you can see that's the difference between the California minus the treatment group, minus the synthetic control, sorry. Right, so it's California minus synthetic control. And you can see almost perfectly pre-treatment, it's pretty close to 0. Sometimes it's a bit higher, sometimes it's a bit lower, but on average it's very similar. And then you can see a huge drop at the time of policy. The only thing that might be concerning is that you can see it kind of starts to drop off even before the policy was implemented. So there might be a bit of anticipation effect. But I mean, I don't think that would matter too much because we're only taking the difference in the after period, right? So we're not, when we do a difference in difference and there's anticipation effects, you're concerned that they've already responded to the policy before the policies happen. So when you difference off the before policy outcome, it's already lower than it should be, right? So in this case, it doesn't matter as much because we're only taking the difference in means in the after period. Okay, so you can see that basically the smoking policy, Proposition 1999 in California, has decreased per capita cigarette sales by about, I would say like 28 packs by like 2000. I mean, if we're looking directly after the program, I would say maybe 10. Okay. Any questions about this graph? Okay. So figure 3, oh wait, that is, okay, we just looked at it, so yeah. Figure 3 is suggesting that Proposition 99 had a large impact on per capita cigarette sales and the effect increased over time, right? So the magnitude here, right after the policy, was only like 10 packs per capita, and then it gets larger and larger. So maybe it really did take time for like these attitudes to change. Obviously, smoking can be an addiction, so it might take time for smoking patterns to be reduced. So they estimate a decline of about 25% of cigarette consumption from this policy. Okay, so what are the concerns for validity? Well, it could be the case that the increase in anti-tobacco sentiment created by California from this policy, it might have spread to other states, which would be a spillover effect, and that would contaminate the donor pool. So what is the problem with a spillover effect? We've talked about this before in randomization. You guys remember? What's the spillover effect, even?
When the effect on, well, a program, for example, affects not just the treatment, the treatment group, but also the control group.
Yeah, exactly, Helen. So a spillover effect means that our treatment effect is spilling over onto our control group. Same thing, Susanna. That basically your estimates will be over understated because somehow the control group is receiving some of the treatment effect, right? So if some of the control states benefit from this California anti-smoking policy by also reducing their own smoking, then our results could be understated because then also the control group will see a reduction in smoking. So then we look at the treatment effect, it's smaller than it actually would be. On the other hand, like maybe we overestimate the treatment effect if, as we said earlier, everyone who smokes in California is now going to control states by their cigarettes, right? So that would be an increase in cigarette sales for the control group. So that would actually really over bias our estimates. So those are both different types of spillovers that might affect the author's estimation. And it definitely is concerning. Like, it seems reasonable that some people would drive to California if they live, or to another state if they live close to the border. But I don't know how much of the population would actually do that. So yeah, that would definitely bias the estimates. Okay, so another concern is that maybe in response to Proposition 99, the tobacco industry in America could have used funds that were supposed to go to advertising in other states towards California, right? So since this policy was so large scale, like, you know, guys know that big tobacco, they have a lot of money to throw around. So if they see this policy is being implemented, maybe they'll spend extra money on campaigns and advertising to try and increase tobacco sales in California. So that's definitely possible given how large of a program this was. Either way, it would definitely bias our estimates. Okay. Yeah. So on the other hand, it's possible that the rise in tobacco taxes, okay, I already talked about this, increased cigarette smuggling. So buying cigarettes from another state that has lower taxes, and that would be a spillover effect as well. So the authors want to be sure that these estimated effects are true. They want causality, right? And so they want their estimates not to be driven by chance. So to do this, they're doing some sort of falsification test to answer the question, how often would they be able to obtain the results of this magnitude if they'd chosen a state at random for the study instead of California? So this is a placebo test. That's what they call it. And we've talked about placebo tests for difference in differences, but this is one for a synthetic control. So what they're doing here is that they are basically saying, using the same analysis that they did for California, right? So they had California, they created a synthetic control group and compared their post-treatment outcomes. So they're going to do this, but instead of California, they'll choose random states that did not receive a tobacco program. And so what they would expect to see is that there's not a significant effect on smoking because they had no policy, right? This is a placebo test to make sure that the methodology is working well and that it's reporting a true causal effect for California when there is one and not just for any state randomly at luck. Okay. So obviously we would expect that only California sees a big policy effect because they're the only ones that actually did receive a big policy change. So the other treatment groups that we choose at random for our placebo test, they really should have an effect size at 0 or close to 0 on average. So following this procedure, they conduct their placebo test. And like, as I said, they choose states that didn't get the tobacco program implemented. And if the placebo studies create gaps of magnitude similar to the one estimated for California, then they really can't say for sure that their effect that they found of Proposition 99 is causal, because it could have just been luck. So yeah, if the placebos show that the gap estimated for California is large, like much larger than the other placebo tests, then they feel confident that their results is causal and that it's a true effect, not just random noise. Okay, so this is what they have. So obviously this dark black line is California, and then all of these other ones are their placebos. And each placebo has their own synthetic control made for them. I don't know, what do you guys think of this? I want your opinions. There's a lot of lines. It's confusing. I totally agree. Yeah, so there are a lot of lines because they're doing it for all of the other 38 states. And so what the authors say is they're really happy about this graph. They think it's awesome because you see how California is one of the lowest lines that you see. So they're saying we see a much larger effect when we have the California policy compared to when we use any other placebo test. But to me, I'm like, what are you smoking? Because there's so much variation, and like there's so many lines that receive almost a similar effect, like down here. And there's also some policies that see a large jump in smoking compared to their synthetic controls when they haven't had a policy either. So to me, I'm just like, there's a lot of noise here and variation. So maybe they would be overestimating the true effect using this strategy, but it could just be that the some of these other states might not be good controls if they had other policies at similar times that the authors aren't controlling for, right? So I don't know. It's a hard, like you would really have to argue it well, but I mean, this is a really famous paper and it seems to be accepted the results, but this placebo test is not super convincing for their argument. I'll say that much. Okay. Oh, that's all the slides. Oh, wait, what? Oh, wait. So then they do it again. I think they clean it up a bit. So this, oh, wait, no. This is figure 4. Oh, so basically what they do is reduce their sample size to get a cleaner result. And so they drop states that have a high mean square prediction error. So that's just a mean square prediction error is basically they will make predictions of what the post-period cigarette sales should be based on pre-period, and ones that deviate far from the prediction, they just drop. So I don't know if that's actually valid, but that's what they did, and it looks a lot better. I mean, California does see the largest effect across all of them, but I mean, there is still some pretty close in magnitude, which is concerning. So would you guys, since we're all economists here, what do you guys think? Would you accept the results of this paper? And do you think they estimated a true effect? Quite acceptable. Says it's quite acceptable. I mean, I'm kind of convinced by it just because their pre-trends are so good. Like when you look at how comparable the characteristics were to smoking, it seems good. I would just be concerned about time shocks, right? Because I don't think um they don't add like fixed effects. So I think I don't know if you actually can add fixed effects to a synthetic control because it's synthetic, right? So that might be a downfall. Because imagine if there's a bunch of shocks happening over time in these other states. Like they're looking over a long period. They're looking from 1970 to 2000. If you're telling me states don't have other shocks that might affect this outcome, that's just craziness. So I think that's the one downfall is that they don't have fixed effects to control for other types of shocks. And that's where I think we see these large jumps in different outcomes. So, but yeah, that's just my opinion. What do I know? Okay, so then the other one is this is more convincing. They show the distribution of ratios of the post-pre Proposition 99 mean square prediction error. So as I said, like they're predicting what they think the post-period cigarette sales should be based on the pre-period. And if the deviation for that state is really far, that means that they have a really high prediction error. So you can see here, these are the prediction errors for pre-post for Proposition 99. And you can see California has the highest prediction error. So that's really comforting because that's showing that there must have been some policy change that created the post Proposition 99 cigarette sales to be so much higher or so much lower than they were in the pre-period, right? Because there's a huge mean square prediction error. And we really don't see that for very many other states, maybe 3 others, but most of them have a very low error. So that definitely is more comforting to look at because it does show that there must be some sort of treatment effect. And you just hope that they estimated the right one. So yeah, those are all my slides for chapter 5, which we covered difference in differences and synthetic controls. I did have event studies design in there and I talked about it quickly, but I just wanted to focus on these other two. I think synthetic control is maybe more widely used and interesting. So yeah, that's why, and we're running out of time this semester. So we're going to be moving on to regression discontinuity design. But if you guys have any questions now, let me know. Okay, so for the last 10 minutes of class, I just want to show you guys how to run this command in Stata. Okay. So this is the smoking data set. This is actually from the paper, and they actually have it on, it's already loaded on Stata. So they have it as synth smoking. It's system use and smoking, so you guys can access this data set as well. It's just in this data. So I have it here, and so what I'm doing is just setting the data set to a time series. Did that even run? Is this even the right data one? Oh, here it is. I have a bunch of this. Okay. So yeah, to run a synthetic control, it's actually pretty easy. So the command is synth. So it's just SOC install synth. And it's important that you declare that you have a time series. So then to construct the synthetic control, pretty simple. So you can see here, I don't know what I did with all those. I think those are estimates or something. But anyways, Actually, I'm just going to clear. I don't know what all these other variables are. Okay. Never like showed my coding before. This is like, I don't know, it's really weird. I don't like it. So yeah, so this is the data set. So they have state, which is the state, I think it's name, but I'm not sure. So I'm just gonna go tabulate state to see what they look like. Okay, so yeah, they just have state name, so all the states that are included. And then year, we know that year goes from, I'll just go somewhere, summarize. Okay, so yeah, year goes from 1970 to 2000, and then we have cigarette sales, the log income, so GDP, and beer. And then also, this beer is beer consumption per capita. And then age 15 to 24 is just the percentage of the state population in that age category. And then RET price is the retail price of cigarettes. Okay, and then you can just browse your data. I like to do this. So it's ordered. Oh. I'm just going to sort it by year. Okay, so I just sorted it by year. So you can see that there's some missing values. So you can see the GDP and beer is missing. Well, income's missing up to like 90 or 72, and then beer is missing up until 84. Okay, and then I think it's after this 1990. So in the after period, like remember that treatment was in what year? 1989. So we only care about these predictor variables like smoking, or sorry, not smoking, like beer, law and income. All of those variables only matter to us for the pre-period. So anything before 1989, because we're not using them as outcome variable, we only need them to form our synthetic control. So anything missing for those variables in the after 1989 doesn't really matter. Okay, so to do your synth, the command is literally just synth, and then sigsail, which is our dependent var. And then, so this example, I'm putting beer, but from 1984 to 1988, because remember that the variable beer is, we're actually missing data up until 1984. So you don't have to do this, like it will just exclude the missing data anyways, but I just put the average from 1984 to 1988, and then law and income, retail price, age 15 to 24. And then also, as in the paper, they use cigarette sales in 88, cigarette sales in 1980, and in 1975 as the predictor. So we're including that. And then you put treatment unit 3 because that's what California is, the treated unit, third treated unit. And then treatment period is 1989. Okay. So let's do that. So it automatically does nice things. So it gives you the control units, treated units. So a treated unit is California, and then all of the control units here. The dependent variable is cigarette sales. Mean square prediction error minimized for periods 1970 to 1988, right? So those are all of our pre-treatment periods. And so they obtain results for all of the years 1970 to 2000. Okay, and then these are our predictors. Okay. And then they're averaging over 1970 to 1988, unless specified otherwise, which we did for beer. Okay, so you can see that this gives all the weights to the different states, like we saw in the paper. So a lot of them have zeros, but we see, well, I mean, this is from the paper, so it'll be the same, right? So there's weights for Colorado, Connecticut, Nevada, and Utah. So it's the same as we saw in the paper. It's the same data set, go figure. And then it shows predictor balance. So this is the balance table. So yeah, you have your treated and synthetic. So they're slightly different, but I mean, it's not bad. Okay, so that's your balance table. And then what actually matters, like we all care about when we do a synthetic control, is the figure. So to do that, you just have to go add fig to the end. Fig for figure, and that will just give you the result, but with a table, I do believe. There it is. Okay, so this one isn't as good. I don't know why. There's probably some data that needs to be cleaned first. So you can see that this produces the graph, which is the synthetic control group. And yeah, this is your pre-trends. Obviously, they're not perfectly aligned like we saw in the paper. I think they did some cleaning. And this is the basically treatment effective interest. This is the post period, right? So we have set our treatment period to 1989. So this is post, and then this is everything before. Any questions with that code? It's very, very, very straightforward. Okay, if you don't have questions, I'm gonna leave you there, and I'll see you guys on Monday. So next week, Wednesday, I think we're having a guest lecture again, Vadim Marmur. He's gonna be teaching us about like regression trees and machine learning. And so he's gonna be working in R and I think he'll send a data set so that we can work along with him if we want, or just watch. But yeah, so that'll be super cool. I'm very excited about that. I do not know much about machine learning, I'm going to be honest. So should be fun. Okay, great. So if there's no questions, I will try and finish up your grading for assignment 2 this week and send out your last assignment for the semester. Okay, have a good night, everyone. Bye.